So our next speaker is Omry Ginzburg. He will be talking about accretion-driven turbulence in early disks, a controlled experiment.
Yes, so hello. It's hard to top a talk after Andy. So much energy, but I'm a bit more tired than him, I guess. So hi, I'm Omry. I'm a PhD student at the Hebrew University with Avishai Dekel, and today I will not continue, take the topic that Andy started talking about to slightly, what I think, a parallel direction. So this is work done with Nir Mendelker and Frederic Boudneau as well. So I'd like to start the motivation with two main properties of star-forming disks that I care about. One is the structure. So simulations and observations, especially at high redshift, show that the star-forming disks are extremely perturbed, many giant clumps, star-forming clumps. So these candles, galaxies, Baguo, and the Villa simulations, and a very disturbed structure, which we've seen from Andy as well. The second property is the supersonic turbulence. And again, in observations and simulations, especially at high redshifts, you have very supersonic turbulence of the order of 50, sometimes even larger kilometers per second in velocity dispersion. Now, Andy did a spoiler to what I wanted to show, but to talk about is these two things are actually quite deeply connected. And the link between them is the concept of this self-regulation and the two-main stability. So, okay, two-main stability, Q, presents a competition between two outgoing pushing forces and one ingoing pulling force. And when Q is above 1, the disk is stable. The Q below 1, the disk is unstable. And I want to present a qualitative picture, which is not as quantitative as Andy showed, about why with the concept of self-regulation, why we think Q should be actually somewhere about unity. And let's look in a heuristic way. So Q is a function of time. This is a Q equals 1 line. And let's assume we have a galaxy, a disk that starts with a value of Q slightly below unity. Then we have clumps, we have asymmetries in the disk. Once you have asymmetries, you have torques that should drive radial inflows down the potential well, converting potential energy to kinetic energy. Furthermore, in the clumps that form, we have intense star formation, we have feedback. Both of them are able to feed up the turbulence with energy, driving the velocity dispersion above unity. And one of the key things is that in order for the disk to not completely disappear, you also need a continuous supply of gas in order to keep the surface density reasonable. And this is why just sigma going up is enough to bring Q above unity, because you have constant supply of gas. Once Q goes above unity, the disk becomes gravitationally stable. We have less clumps, less torques, less inflow, weaker star formation in very dense regions, and the turbulence is able to efficiently dissipate, bringing again the velocity dispersion down, Q below unity, and so on. The cycle continues. So maybe the value of Q of 1, this is an idea. Maybe it's slightly below, slightly above, but around this order unity. So we can see that the structure and the gravitational instability and turbulence go really hand in hand. And they're doing so by the interplay between turbulence driving and turbulence dissipation. So turbulence is really a key structure or key concept that determines the dynamical and structural evolution of the galaxy. So what can supply energy to turbulence? So we talked about supernova feedback. We talked about transport. Here are maybe other processes that are able to drive turbulence, and I want to focus on cosmological accretion. By cosmological accretion, I mean this. This is an animation that Avishai really likes to show a lot, of a cosmological simulation, a very old one. I think it's 20 years old, that's showing a massive galaxy being fed by 3 streams. So when I talk about cosmological accretion, this is what I have in mind. So usually 3 streams feeding a massive galaxy. Now, cosmological accretion can help turbulence by 2 ways. One is by feeding gravitational stability, but this is not the process I'm talking about. I'm talking about direct deposition of the kinetic energy that is carried by the accretion to the disk. So this is a different process. This question has been asked actually by Andy himself as well. in several studies. These are just a few. And these are the resolutions of each study on how important is the role of this type of driving in the evolution of a galaxy. So it ranges from, it can be very important to maybe it's not important at all. Last year, in collaboration with Mark Rumholtz as well, we developed an analytical model for the evolution of gaseous disks under the assumption that turbulence dissipation is balanced by three drivers that I've just mentioned: supernova feedback, transport, and accretion. By transport, I mean the inflowing of gas down the potential well. And the way we modeled accretion-driven turbulence is by assuming that some fraction of the kinetic energy flux carried by the accreting material is converted to turbulence, while the rest is either going to the bulk motion of the rotation, for example, or immediately radiate away in shocks. So this is this parameter psi A. This parameter will depend on many, many, many things: the stream density with respect to the disk, the orientation of the accretion with the disk, the geometry of the stream, if it's more cylindrical, if it's more spherical. And it's not very clear what this value is. Several studies assume several different values and got different results. So in our paper, what we wanted to do is to, as a function of mass and redshift, understand which of the three drivers is the dominant one, because this tells us how the nature of the turbulence in the disk. And the way we did that is by looking in this plane. So the vertical axis shows the ratio between the rates of energy injection to turbulence by transport to that by accretion, and in the horizontal is that by accretion compared to that by feedback. And if you think for a second, you realize that the plane is divided into three regimes, each in which another different driver is a dominant driver in the sense that it supplies the most amount of energy to turbulence. So we wanted to see as a function of mass and redshift, where do galaxies fall in this plane? And what we did, we integrated the equation I showed you before and plotted evolutionary tracks of galaxies according to the results of our model. The nice thing about this kind of models is that the evolution is uniquely determined by the halo mass of the host halo at redshift 0. So this is the value that you see here, 10 to the 11.5, 10 to the 12, etc. The gray region, I don't want to get into the details, but this is where you should take our model seriously. And if you're interested, I can tell you about the origins of this gray region. But for now, focus on the position of the tracks only when they are inside the gray region. So the picture that we find is that at high redshift, say above 3, above 4, we have that all of the disks are expected to be in the region where accretion is the dominant driver. At intermediate redshifts, except for very low mass disks, transport will be the dominant driver, and at very low redshifts, except for the very massive disks, feedback is the dominant driver. Using our models, I just want to show some comparisons to observations. So we compared the velocity dispersion star formation rate relation. This became a canonical way to see how turbulence is driven by disks. And given the huge uncertainties in the observations here, if you put the error bars, you can't read anything here. We get a qualitative agreement between the curves that our model predicts compared to the observed dots. Now, going back to the model, we assumed a very specific parameterization for this parameter psi, which was completely ad hoc. Because we don't really know how it behaves as a function of mass and redshift, we assumed some redshift parameterization that captures what we thought should be the trend with redshift, but it wasn't really justified, and this is the subject of the current work that we are doing. So in order to study this, the efficiency, I'm going to show you a movie while I talk. We run simulations of isolated galaxies using Ramses, in which we have a massive disks that we by hand feed with streams. And we do that by defining 3 cylinders, because we believe there are 3 streams feeding massive galaxies that inject mass, momentum, and energy into the simulation box. We still don't have star formation and feedback, obviously, because we still need to understand the simpler setup before we move to a more complicated setup, which is not very easy. So this is how the galaxy evolved. And you see that if you have accretion, you have a more smooth component and not only a very clumpy one. So, so we ran a couple of suites of simulations. Each of them have a varying mass accretion rate, and the way we chose the properties that determine this accretion rate is first by assuming that the stream velocity is roughly the disk rotation velocity. This is what you expect from cosmological simulations and what you expect. For a fiducial model, for fiducial simulations, we took the density of the stream to be that of the outer disk. And if you want a doubling time, which is the typical accretion time, to be of order 1 gigayear, which is what you expect for redshift 3 or 10 to the 12 halo, you are left with a 3 kiloparsec stream radius. We then took this fiducial value and ran a few simulations varying this density between each simulation. So from 2 times larger to 20 times smaller, to see how, for example, the density affects things. If you look at, the reason we first played with density is because if you think about simple momentum conservation, higher density contrast leads to less thermal losses by shocks, radiation, compared to low density contrast. So the momentum conversion to the disk turbulence is more efficient when you have a high density contrast. So if we look at the kinetic energy in the turbulence as a function of time, you can really see in the 3 simulations of the highest density contrast that they really have more energy more kinetic energy in turbulence. And if you look at the simulations with low values, you can say when comparing we have no accretion, that there is no much difference. So you can say maybe accretion is not efficient and not important in these simulations. However, according to our model, once you introduce more drivers of turbulence, the role of gravity actually goes down, and with accretion, actually it goes down pretty fast, if you assume some sort of self-regulation. So even though the energies in turbulence is similar to that with no accretion, the role of gravity actually is expected to go down and have more effect from accretion. And we'll need to quantify that, but we still haven't quantified the role of gravity. Another thing you might say is that, well, if you go here, you add more mass, as everything else is fixed, you add more energy, so you might expect this spread in energies, which is correct. So we ran another suite of simulations in which we fix the input energy. So we do that by changing the velocity, and you still see some dependence on the density contrast between the stream and the disk. So the density of the stream is really important when we look at the efficiency of driving turbulence. One simulation here is missing, that with a 2 times density. For that, we did another preliminary experience, and we shrunk that stream. We made it 3 times thinner, but increasing the density, but again, keeping the input energy fixed. And we can see that this actually, if you compare it to the previous energy of this kind of stream with twice the density, actually produces less energy in turbulence. So the stream diameter or the cross-section interaction between the stream and disk might actually have an important role as well. Finally, just to convince you that the way that I think that the turbulence generated by the accretion is not by fueling gravitational instability, we looked at the power spectrum of the velocity field in each of the simulations. And we have 2 scales. One is what you expect if gravitational instability is able to drive the turbulence, is the scale of roughly the disk scale height, which is 1, 2, 3 kiloparsecs. But if you look at the streams, especially the simulation with the streams with the highest densities, you see actually another scale that emerges. And that is roughly the scale of the stream diameter. So this hints you that the mechanism that drives turbulence in this disk is not only gravity, but can actually be the actual interaction with the stream in the disk via shock instabilities, Kelvin-Enno instabilities, stuff we should look at. So I actually went faster than I needed. Okay. So when we talk about disk instability and self-regulation, we need gravity, we need supernova feedback and accretion. And I hope I'm convinced you that accretion drives turbulence in a distinct way than gravity, and we've seen it from the power spectrum. The efficiency depends, and we still need to prove that, on density and cross-section, and more stuff that we should look at. And finally, what I learned in the last year is gravity is a mysterious thing, and we actually don't really know how it works in disks. And if Genzel was here, we maybe had more of interesting discussion on this. But you see in Andy's talk and you see in Drupa's talk, next to me, after me, that gravity does not work as we think it should work. Thank you.
Thank you for the really interesting talk. I was wondering what were your expectations if instead of having just 3 filaments pointing in exactly the same direction as function of time, they were moving, because when you look at cosmological accretion, you don't really expect the filaments to just be like cylinder pointing in a steady direction, especially in like hundreds of million years.
The time scale of this wiggling will be very important, because if it's very fast and the angle is too small, I would suspect that it will not be very, very important. But if it's slow, eventually, if the time scale is longer than the typical time scale it takes the disk to reach an equilibrium, I actually also don't think it will be too much. Unless you are talking about really changing the impact parameter from positive to negative and back. I don't think that will have a major role, but that's something we should actually, I was talking with Andy the other day and he also suggested this. So that should be looked at as well. The parameter space is huge. It's a very ambitious thing, and I hope I can get something out of it.
And next speaker can sit up.
Do you want?
Nice talk. I just wondered if infall occurs in the outskirts of galaxies, in an inside-out growth of galaxies, then you would expect the outskirts to be driven by the infall velocity and the inside be driven by feedback, supernovae, and so on. And that should make a change then in the velocity dispersion, or what do I know, because these are 2 different processes. Do you see something like that in your simulation, so that in the outside you have big wobbling and warping disks because of all this infall?
So I did look at the velocity dispersion profiles. I would agree if the impact parameter really is not the disk radius. So it's smaller. So I think the accretion affects both the inner parts and the outer parts together. But if it will be more tangential, then we'll see, I think, a difference. If I look at the profiles now, I don't see a big difference between the inside and outside.
Okay, we thank Omry again.